So here we are, and this is a typical example. We have a barrel that's filled with a fluid that has a density of 4 kilograms per cubic meter. Let me just do it anyway, okay? So the barrel is open to the atmosphere. The atmospheric pressure is 80 pascals. And what's the absolute pressure? 3 meters below the surface. So I'm visualizing here, I'm saying, well, the atmosphere is 80 pascals, so let's put that down. That's a bit unrealistic. It's more like 100,000 pascals, but, you know, whatever. And this is 3 meters. And what's the absolute pressure? So P absolute is equal to P atmospheric plus P gauge. And this equals P atmospheric plus rho GH. It's the density of the liquid in kilograms per cubic meter. So it's your mass density. Sometimes people give you their weight density, which is in newtons per kilogram, in which case you don't need G. So don't get caught by that. There's two types of density. There's the mass density, which is much more commonly used. But then there's the weight density, which is basically the mass density times G. It's to get the kilograms into newtons. And if that's the case, you only need to multiply by the height. So we say P absolute is equal to the P atmospheric, which is 80 plus, and my density is 4 kilograms per cubic meter times G, which is 10, times my height, which is 3 meters. So P absolute is equal to 80 plus 120, which equals 200 Pascal. Simple as that, basically. It's terminology, isn't it? It's not the math. It's never the math. It's the terminology. It's knowing what they're asking and how to interpret the words. This leads us to using columns of fluid as useful pressure gauges. Pressure is force per unit area, but they didn't know that for the longest time. They just knew there was this thing called pressure, and they wanted some way of characterizing how big or small it was. And so they characterized it by its effect on a fluid. And the simplest way of characterizing it is to look at the change in the height, if you like, the difference in the height for the fluid in a U-tube manometer. So this is basically just a U-tube filled with fluid, and if you leave it alone, the fluid finds its own level, but if you push on one end, if you blow on one end, it goes that way, and if you suck on the other end, it goes that way. So we have our test pressure here. We want to find out how it compares, how much pressure is in there. First thing we see is that it's more than atmospheric, because this is open to the atmosphere and we've actually pushed this end down and that end up. So the balance point is when the atmospheric pressure plus this gauge pressure is equal to that. So we can get our height by measuring from the lower level to the upper level. And we say our test pressure is equal to our atmospheric pressure plus our gauge pressure. We just basically looked at that. Then the interesting thing is, supposing that I could not have to worry about the atmospheric pressure because day by day atmospheric pressure changes. Supposing I could only concern myself with the gauge pressure. Well, there is a way you can do that. And what you do is you don't take an open tube, you take a closed tube like a test tube, and you lay it in a fluid so all the air comes out, so it's completely filled with fluid. And then you turn it right side up and you start pulling it up through the surface. So if I draw a diagram here, I'm not going to be able to draw it very well, but here's my test tube. It's got no air in it, and it's still filled with fluid, and it's still filled with fluid, and it's still filled with fluid. And I get to this point where I start seeing a surface appear. And then I see, and that surface doesn't change. And what that tells me is that pressure, the pressure caused by that column of fluid, is equal to the atmospheric pressure. And what's inside this gap? Nothing. So we call this vacuum. No gas particles to speak of, no pressure pushing down, just an empty space. So now, for this, my atmospheric pressure is equal to my height of my column of liquid times rho times g. So this is a way of measuring the atmospheric pressure. So it's really quite nice. If I wanted to do this with mercury, I would use 76 millimeters. I would need a tube which is more than 76 centimeters tall, about basically 2 feet, maybe 3 feet. If I did this with water, I'd need a tube that was more than about 30 feet tall because of the difference in densities. And so when people started measuring pressures, they used the units that were naturally occurring, which is centimeters of water, or millimeters of water, or inches of water, some way of measuring that height, or centimeters of mercury, or inches of mercury, or millimeters of mercury. The millimeters of mercury got used. It was a nice combination. It's the number you get for atmosphere is 760, and you can measure in like 1/760th of an atmosphere. So that actually got named after a famous vacuum scientist called Torricelli. So it got called the Tor. And so it went on. None of the early units had anything to do with force per unit area because they didn't understand that that's what they were looking at. It just had to do with the height of a column of liquid. And we inherited that to this day. The ones that don't, the Pascal, which is the Newton per square meter, or the pounds per square inch, if you think about it, is much more physically relevant. It's in imperial units, but again, it's looking at some idea of a force over an area. So, barometer, open tube manometer, we don't use these anymore. The water one was too big, too cumbersome. The mercury one was actually all right, and many houses, if you wanted to buy somebody a present and you couldn't think of what to buy them, you'd buy them a little gauge which they'd hang on the wall, and it would have a thermometer in one part and it would have a barometer in the other part, and filled with mercury. Which is not a good thing to have around, kids especially, but certainly not a good thing to have around your house. And at USF, I remember disposing of a whole bunch of mercury barometers, and there was so much mercury in those things, it was untrue. It was, and we found out that, inevitably there'd been, people had dropped these things in classrooms, and so there'd be mercury in the tiles. We found, from years and years ago. Open tube manometer is filled with a fluid that has a density of 6 kilograms per cubic meter. A cylinder of compressed gas is connected to one end of the tube, and it causes the height difference of 4 meters. Atmospheric pressure is 300 Pascal. Again, not realistic numbers, but reasonable. So what is the value of p-test? And can you have a go at that for me, please? And I'm gonna turn off the recording. So here it is. We basically looked and said, well, we recognize that p-test, well, that's just the absolute pressure. So that's going to be atmospheric plus our gauge pressure. Atmospheric we're given, that's 300 Pascal. Gauge pressure is rho GH. We're given rho. We're given H somewhere. And we know G's 10, so it's plug and chug at that point. It's fine. Barometer is filled with fluid that has a density of that. Atmospheric pressure causes a 5-meter tall column of fluid to stand above the reservoir. What's the atmospheric pressure? I'd like you to have a go at that, please. So let's resume. So basically, let's visualize first of all, and what we have is our inverted test tube in a bucket of fluid, and this has a vacuum up here, so there's no atmospheric pressure pushing down. So our atmospheric pressure is balanced by this column of fluid. So now we can say that our P atmosphere is just equal to our P gauge. So our P atmosphere is equal to rho GH, and our P atmosphere is equal to our rho, which is 8 kilograms per cubic meter times 10 for our G times H is 5. So P atmosphere is going to be 5/8 of 40, 400 Pascal, which is that guy. So just a little bit of, so you've got to be a little bit careful. You've got to visualize. So before, when this was an open tube, the atmospheric pressure was what we referred to as pushing down on top of the column. And we had an absolute pressure, which was the total effect. And now we're talking about the atmosphere being the other side of our equation, because we're trying to use this column to measure the atmospheric pressure. So just watch out for that. P atmosphere is the subject of this equation, whereas P atmosphere was one of the things that gave you the subject of that equation. So it's an atmosphere in a different place, if you like. Okay. Bit of a line, Pascal's principle. If you put fluid inside a enclosure, so there's no air, then we get this weird situation where we find that the pressure is the same all over it. We say consider a system consisting of 2 cylinders of different cross-sectional areas. The cylinders are connected together by this little tube. The system is in equilibrium, so the two things are just balancing each other. Pascal law states that the change in pressure applied to the fluid is transmitted undiminished to every point of the fluid and the walls of the container. What that says basically, and this is what basically Pascal's principle says, is that the pressure here on this left-hand syringe piston is equal to the pressure there on the right-hand syringe piston. Not because at the same level, but just because they're touching the same fluid. So the P on the left-hand side equals pressure on the right-hand side. Now, if we remember that pressure is the force per unit area, so we have force 1 over area 1 must be equal to force 2 over area 2. Okay, we just used, the definition of pressure. Here's the really interesting thing, though. And this might not be so obvious. A little force over a little area effectively can balance a huge force over a huge area. So I can literally put a car on one side and I can use my thumb on the other, and I can balance the car with my thumb, because my thumb is weakly pushing down on a really small area and the car is strongly pushing down on a huge area. As long as those ratios are the same, everything's happy. It seems like you're getting something for nothing. But that's what machines do. Simple machines basically enable us to use small forces in place of big forces, provided that if I'm trying to do something, not balance something, but do something, I do the same amount of work. So, yeah, let me jump in a little bit here and say what I can use this for is not just balancing things but lifting things. So let's say you go to the shop, you go to the auto shop, and they want to put your car onto a lift. What they have is they have a machine that looks a bit like this. There's a piston on this side, and your car basically sits on that side. And here they have another piston. And what they do is they use a little motor just to push this thing down. And in pushing this down a long way, they lift this up a little way. Because the amount of volume in this system is always the same. So if I want to raise this by a certain amount, I got to provide that liquid by having this descend by a certain amount. So a little force through a big distance gives me a big force through a small distance. Let's do that like that. So in terms of work, I'm not getting something for nothing, but I'm able to use a small force on a small piston to affect a big force on a big piston. And it is quite eerie. You can actually get a machine that has a big piston and a small piston and use your thumbs, and your thumb pushing on the little piston can always overpower the thumb pushing on the big piston. And it just seems like weird that one thumb can beat the other thumb, because it's not often that happens. This is used in jacks for a car sometimes. Sometimes it uses leather. Sometimes it uses this. It's used in hoists. Used in a whole bunch of things. We use this. So let's look at a problem. A hydraulic system consists of one cylinder that has a cross-sectional area of 4 square meters, which is connected to another cylinder that has a cross-sectional area of 12 square meters, and a force of 9 pounds is applied to the smaller, 9 newtons, sorry, is applied to the smaller. So then what force can act on the bigger, so F? Can you do that for me? So our principle is Pascal, which is pressure on one side equals pressure on the other side. And that means that the force on the one side over the area of the one side equals the force on the other side over the area on the other side. So then 9 over 4 is equal to my unknown force over 12. And so rearranging, I get my force is equal to 9 times 12 over 4. 4 goes into 12 3 times. 3 9s are 27. So that should be 27 newtons, which hopefully is there, yeah. Cool. So not bad. Just word to the wise. So how can I make this a little bit more, general physics level? We showed the principle, but how can I dress it up so that it's not just like 4 numbers and you substitute in? What can I do to check whether you're thinking as a physics person or just substituting numbers into an equation?
Well, you have 4 and 12, so there's a 1 to 3 ratio.
So I could give you a ratio question on it. Yeah, if I triple this, if I triple the area, what does that do to the force? That's 1.
You can give us weight instead of newtons.
I could give you, well, no, weight is newtons. I could give you in pounds, I guess.
Well, pounds, not weight,
Yeah, and I tend not to do that, and maybe I'm wrong on that.
I don't even know how many that is.
So I'm wrong on that because I suppose when you go to engineering, some of those people still work in pounds, but I just feel like, it's like none of the rest of the world does. So
Pounds to, I'm gonna have to prefer pounds to.
it's just a conversion, but it's just I choose not to do it.
I'll never get
But there's something much more straightforward that I can do. That for me is just like, I love doing this because it's amazing.
You will not give us the actual area.
What would I give you instead?
The radius.
I would give you the radius. Very good. And just to see, so have you finally learned that the area is pi r squared as opposed to 2 pi r? I got physics 2 people who still refuse to learn that, And secondly, the other thing I could do is I don't give you it in square meters, I give you in square millimeters. So there's 2 little other additional things I can just push you on a little bit. And yeah, if you know the equation, you'll get a little bit of credit for it, but, you know, we expect you to get the right answer. So remember, you know, it's kind of like we're showing the principles, but there's, on game day, you got to be a bit more on your game. This is same thing. I'm not going to bother about that.
The next one has a radius.
Oh, is that right? So the next one I had the radius. So I'll leave you to have a go at that. So next, let's look at buoyant force and weight. So now we're dealing with objects that either float in or submerge below the surface of a fluid. And we've all had some experience of this. If we've been swimming, we've had some experience of this. If we've gone sailing or if we built rafts as a kid, we've got some experience of this. The problem is we've got some experience of this, which is not necessarily the experience I'd like us to have. Some of our language is a little bit loose. We probably all talked about buoyancy. Does your boat have enough buoyancy? Do you have enough buoyancy? And I'd like you not to talk so much about that, or at least not to get it confused with the buoyant force. We'll talk a lot about the buoyant force, and it's not the same as buoyancy. So be very clear about that. Buoyant force is not the same as buoyancy. The buoyancy, in my mind, is the overall effect of the sum of the buoyant force and the object's weight. If the buoyant force is bigger than the weight, you have buoyancy, because you'll float. Well, if the buoyant force is less than the weight, you'll have some buoyancy, although you'd sink. So, you know, buoyancy is the net effect, and buoyant force is the actual thing that's doing the uplifting. And this all came from Aristotle, who supposedly was having a bath. They'd filled the bath up to the brim. There was not one of those little those overflow things you have in most bathtubs. And he got in and the water spilled out. And he realized that he was displacing water. And he realized the water did not want to be displaced. And so he was, by his volume, making it be displaced. And so imagine what would happen if the water was much denser. Well, less of it would be displaced because it would fight him and he would float more on the surface. And he had this inspiration, which was that his buoyant force, the thing that made him lighter in the water, was equal to the weight of the displaced fluid. Because that fluid wants to be as low as possible in the bathtub, and the fact that you're forcing it up means that it's trying to resist you, so it's trying to push down. Well, it pushes down, you go up, you push down, it goes up. There's a bit of a battle going on there. So we need to think in terms of weights for an object and buoyant forces for an object. And we're going to start off by imagining that the object, whether we make it so or not, is underwater, completely immersed. And then we'll look at when part of it sticks out. So we're looking at objects that are completely immersed. And what we say is that the weight, that is, forget about the bathtub, it's just there. Every object has a weight on Earth. So the weight is going to be equal to the density of the object, whatever it is, lead, aluminum, whatever, times G to get it into a newtons per cubic meter. It starts off as a kilograms per cubic meter, then we multiply it by G to get it as newtons per cubic meter, and then we multiply by cubic meters to get it into newtons. So, okay, that makes sense. That equation makes sense. If I have a big density, I get a lot of weight for a given volume. The buoyant force. The buoyant force is the weight of the displaced fluid. So it's about the fluid, not about the object. It's caused by the object, but it's numerically dependent upon the fluid's density. So the buoyant force is the kilograms per cubic meter for the fluid. Let's multiply that by G to get newtons per kilogram for the fluid. Let's multiply it by the volume of the displaced fluid to get the newtons caused by this fluid. And it's trying to get as low as it can, so that's giving me my upwards buoyant force. As you know, I'm a terrible speller, by the way, so this is just a little confession. For years I used to spell this backwards, B-O-U-Y, you know, then B-U-O-Y, and oh man, why did they have the U there? And then I realized that buoyant is somewhat similar to so, you know, hey, it took me 15 years to spot that similarity. Yeah, my name. So, well, maybe I shouldn't complain about being poorly spelled. Picture. I was trying to think of a picture either as a picture or a... Imagine throwing a cubic meter of lead into a swimming pool. Now, imagine throwing a cubic meter of styrofoam, you know, the stuff that we make drinking cups out of, into a swimming pool. This is a gotcha question. Which has the biggest buoyant force? Take me literally. You are going to imagine this thing being thrown into the swimming pool. Don't get involved in math. Think of the reality of the situation. So we have some discussion about this, and basically, so half the people are saying that it's lead will have the bigger buoyant force, and the other half are saying styrofoam will have the buoyant force. So let's think about this. So you throw the lead in, what happens is it sinks to the bottom of the swimming pool, whereas if you throw styrofoam in, it basically floats. And the key thing about buoyant force is it is the displaced fluid. It's not really about the density of the object. It's about the density of the displaced fluid.
So if it has more buoyancy, it has a better tendency to float?
No, because it turns out that buoyancy, as opposed to buoyant force, is about the combination of weight and...
I'm sorry, the buoyant force means it has a bit more tendency to float?
The tendency to float depends upon the relative size of your buoyant force and your weight. And the problem with lead is it has a huge buoyant force, but it's got a huge weight. So this is Fg, and this is Fb, I guess. Whereas here, it's got a tiny weight, Fg. So all it needs is a little buoyant force, Fb. And how do you get a little buoyant force? You immerse less of yourself in the bath. You float, basically. So very interesting. It's not.
So it's A.
So the answer is A, the cubic meter of lead. Which has the bigger buoyancy? Oh, it's the styrofoam has the bigger buoyancy, but lead has the bigger buoyant force. So let's talk about submerged objects. When an object is submerged in a fluid, the forces on the object are the buoyant force and the weight of the object. If the buoyant force is bigger than the weight, then the object accelerates upwards. If the buoyant force is equal to the weight, then the buoyant force is neutral. It's the buoyancy is neutral. It stays where it is. And if the buoyant force is less than the weight, then the object accelerates downwards. Now, because of the water resistance, this acceleration does not cause tremendous velocities. The object reaches a terminal velocity pretty quickly. Or else we could use lakes as like aircraft cannons. We could just put things under the water and fire at planes as they flew over. And we can't do that because in letting things go, it accelerates, but then it reaches a terminal velocity relatively quickly. So we say for a submerged object, the volume of the displaced fluid must equal the volume of the object because it's under the water, so We can only get a displaced fluid volume that's as big as the object. So the two volumes must be the same. But the buoyant force need not be the same. So I've drawn this as the same, and that's a little bit of a misnomer. It could be that. It could be that. Or it could be that. And in this case, it will move towards the surface. In this case, it will kind of stay where it is. In this case, it will sink, depending upon the circumstances. So, but in every case, the volume of displaced fluid is the same as the volume of the object because it is totally immersed. We say a 5 cubic meter block of material that has a density of 7 kilograms per cubic meter is placed under the surface of a fluid that has a density of 9 kilograms per cubic meter. What will the object do? This is a conceptual one. Let's just draw it out. So we have this object is underneath, and the density of the fluid is 9 kilograms per cubic meter. And the density of the object is 7 kilograms per cubic meter. And can you work that out for me, please? So what's going to happen? My intuition tells me that this thing is going to move towards the surface. And my intuition says that because it's got lower density, exactly. So when the object has a lower density than the fluid, it's going to go towards the surface. When the object has a heavier density, like lead does, than the fluid, it'll tend to sink. So, how can I justify that, though? Well, I can say, well, look, it will move dependent upon its relative size of its forces. And here it's FB, and here's its FG. And my FB equals rho GV for the fluid. And my weight is equal to my rho GV for the object. So I can look at this and I can say, oh man, let's just assume this is a 1 cubic meter object. So I get rho fluid. Oh, I've actually got numbers, so I can figure this out, haven't I?
FG is the force of gravity, right?
FG is the weight. No, I'm sorry. FG is the weight. Yes, I'm sorry. So we have for the fluid, it's going to be 9 times 10 times 1, which equals 90 newtons if I assume a 1 cubic meter object. And for the object, it's going to be 7 times 10 times 1, which equals only 70 newtons. So if I have 90 newtons pointing up and 70 newtons pointing down, there's a net force upwards, so there'll be motion upwards. Yes. Question?
Yeah, I have just a theoretical question. What about fish? Their density is not relevant to what we're talking about?
So fish can move up and down in a water column by changing their density, but also changing the amount of fluid that they displace.
And I think they have an organ for that.
They have a bladder, float bladder, that typically they can expand and contract, and they may be able to take water in or not, I can't remember. But that's how they do it, basically. Okay. Yep.
Does the way you work this equation, does it change if you measure density in newtons over meters cubed?
So, there's two forms of the density that we can have. We can have the so-called mass density, which is measured in kilograms per cubic meter. And then we also have the so-called weight density, which is in newtons per cubic meter. So if I'd given you this and said it was 70 newtons per meter cubed, I was giving you the weight density, and you would not use the 10 down here. you'd say that my FB is equal to my weight density times volume, and you'd say my FG is equal to the weight density times volume, and this would be for the fluid, and this would be for the object. So what I do is I pretty well always talk in terms of mass density, and I take weight densities. Oh, I've got to watch out for that, you know. So question or comment?
Doesn't the object have a volume of 5?
Oh, I messed up. So I put that down as 5. I forgot that I had 5. So then this is, I assumed 1, and I should have just kept to the 5.
So since the object has 5 and submerged, the fluid will also have a volume of 5.
That's exactly right. Thank you. Yeah. So I was trying to be too clever, wasn't I? But that actually raises the question that I could give you a question and not tell you what the volume is. And that's no big deal, because you can just assume.
Just use 1.
That's what I do. Yeah. It makes life much simpler. It's like, show that a 3 cubic meter sphere that has a density of 12 kilograms per cubic meter has an apparent weight of 120 newtons when it is submerged in a fluid. Density of that. So first of all, we've got to figure out what the apparent weight is. The apparent weight is what it appears to weigh, and it is basically the tension in this little string. It's that guy. You know, this thing is pulling up on the mass, and this thing is pulling down on the gauge. So it's that tension. Okay. And in this case, I can say, well, the sum of my forces vertically equals 0, so my tension, which is upwards, I'm looking at that bit. My tension, which is upwards, is equal to, I'm looking at that mass. So my tension plus my FB is equal to my FG. Let me draw this out. If I look at that mass, I have, first of all, the gauge is pulling up on me with a tension. And secondly, I have a buoyant force. And thirdly, I have a weight. So I've got to make sure that my mechanics is right. So I've got to remember about, you know, external forces on a mass, and is it in equilibrium or not, and all that kind of stuff. And then I recognize that my tension is my apparent weight, plus FB is equal to FG. Let's put that down. So my tension equals my apparent weight. And it's the apparent weight I want. So my apparent weight is equal to my FG minus my FB.
So what does the AW stand for?
Apparent weight. Yeah. So then I say my AW is equal to FG. And my FG is the density of the object times G times the volume of the object, and my FB is the density of the fluid times G times the volume of the fluid. So my AW is equal to, do I have a density for this object? Object sphere, yes. That's 12 times 10 times the volume minus the density of, so I'm sorry, that has an apparent weight of 120. And so I have, I'm sorry. So I wrote this question when I didn't ask you stuff. I wanted to have the answer in there. And it says, show that it has an apparent weight. So I'm not going to use that as part of my calculation. I'm going to show that the answer is 120. Okay. So now I've got to work out the rest of my answer. So my rest of my answer is the density of the fluid, which is 8 times 10 times the volume of the fluid. What's the volume? Oh, no, it's not the volume of the fluid. Volume of the displaced fluid. Maybe I should put down dF there, but, you know. And that's going to be 3, because it's the same. 12 threes are 36, 360 minus 8 threes are 24, 240 equals 120 newtons. So what does that mean in terms of what we would see? When you had this thing dangling in the air, it would have a weight of 360 newtons. And when you had this thing in the fluid, it would have a weight of only 120 newtons. Because 240 newtons has been cancelled out, cancelled out by the buoyant force. Cool. So I think the hard thing about this is recognizing the fact that you have to use Newton's laws, you were back using equilibrium, and recognizing that the tension is the apparent weight. That's not necessarily obvious. Yes?
How did you get from like the sum of the forces, the tension, and the...
So I recognize that when I have this object, it's in equilibrium, so there must be the wire connected to the gauge must be pulling it up. So that's the tension. And then there must be an upwards force because of the buoyancy of the fluid. Buoyant force caused by the fluid, then there must be the weight. So I did my free body diagram here. And then I applied Newton's first law. Now, what's not clear, I think, to many people is that the tension is the apparent weight. That's the terminology for the same thing.
So in that part, the force, the weight is 0?
Which part are we talking about?
When you plugged in like FG for 0.
FG for 0
Up top,
at the top.
second line.
Second line?
Yeah.
No, FG is that actually.
Oh,
Yeah. So that goes to there, goes to there, goes to there, which actually goes to there. Yeah. Cool. That's not a 0. That's an O for object. Okay. Tried using B for block, but that gets confusing because of buoyancy. So. Floating objects. So in all submerged objects, the volume of displaced fluid by definition must equal the volume of the object. So that's. Now let's take floating. In floating, is a floating object in equilibrium? Yes. Otherwise, it would accelerate upwards out of the water, it would accelerate downwards into the water. So floating object is in equilibrium. You can push it away from equilibrium, it'll oscillate back towards equilibrium, but a floating object is in equilibrium. Floating object, the buoyant force must equal the weight. If we look at the force diagram, the free body diagram, that's it. So the buoyant force must equal the weight. So in this case, we know that the buoyant force equals the weight, whereas before when it was submerged it didn't necessarily. Usually it didn't. And now what's different is the volume of the displaced fluid is no longer the same as the volume of the object. What happens is this thing, if it's floating, must have risen to the surface, and most of the time a little bit of the material sticks out of the top. Because what's happening is, if I draw the sequence, what's happening is this thing is down here and it has a bigger buoyant force than it has a weight. And it has a bigger buoyant force than it has a weight. And then it gets to here and it's still got a bigger buoyant force than it has a weight. And now what happens is, it can't do anything about the weight. The weight is always the same. But it can reduce the buoyant force by displacing less fluid. So it basically sticks enough of the fluid above, enough of the object above the fluid until the volume of the displaced fluid is small enough that it reduces the buoyant force so it's equal to the weight. So it's kind of a clever self-regulating system. When an object is floating in a fluid, the force on the object is a buoyant force upwards and the weight downwards. For floating object, the volume of the displaced fluid must be less than the volume of the object. It could be, I suppose, exactly equal to, but that would be, why would it then go to the surface? Why would it? It's neutral buoyancy if it's exactly the same density. So why would it even bother going to the surface? I suppose you could place it there and it would stay there in theory, but if it goes to the surface, it must have a slightly less density than the object, than the fluid. The object must have a slightly less density than the fluid. And when it crests and cuts through the surface, then the displaced fluid volume must be less than the object's volume because part of the object is sticking out. But the buoyant force must equal the weight. Sphere of 2 kilograms per cubic meter density floats on a liquid that has a density of that. Show that 75% of the object is above the water. Man, this is like incredibly, well, actually it's not. Let's go through it. Let's draw it in its final situation. So here's the fluid, and 75% is above the water. Let's draw it like that. I did a generic diagram here, but let's be a bit more realistic. It looks more like that. That's what it's saying. And here is my displaced fluid volume. So what I have is I have a weight and I have a buoyant force. So I say for floating, let's cut to the chase. The Fg it's in equilibrium, so the sum of the forces must equal 0. Floating, which is equilibrium. So the sum of the forces vertically must equal 0. So my F buoyant plus my Fg must equal 0. So my F buoyant must equal, well, that's enough. Let's just leave it like that for the minute. So then I say, oh, okay. Then my buoyant force, the density of the fluid times G times the volume of the displaced fluid, added to the density of the object times G times the volume of the object equals 0. I know that my weight is pointing downwards, so I'm going to put a negative sign there because it's downwards. So then I say, okay, I got numbers, so let's do the numbers. But let's hold off on the numbers. Let's rearrange. Density of the fluid times G times the volume of the displaced fluid is equal to the density of the object times G times the volume of the object. Let's cancel out what I can cancel. My G's go away. Let's rearrange. Let's rearrange thinking about the volumes. I'd like to, let's say that the volume of the displaced fluid over the volume of the object is equal to, well, that's going to be the density of the object over the density of the fluid. Well, this equals the density of the object is 2 over the density of the fluid is 8, which is 0.25. Now let's think about it. That volume over the total volume is a quarter. That's telling me that a quarter of the object is below the water. Agreed?
Yes.
So 25% of object is below the surface.
Which means the rest of it is.
So 75% of object is above the surface. Proved. Okay, so now we go to the fun bit, dynamics. We don't talk much about dynamics because it's very hard. Well, we do two things in dynamics. Dynamics is divided up into two bits. We have what's called laminar fluid flow, and we have turbulent flow. And the problem is, if you turn a tap on and you just let the water dribble out, not drips, but a steady stream, that's laminar flow. That's beautiful. If you just blow nice and gently, that's laminar flow. If you turn the tap on full, you get a sputtering. That's turbulent flow. Turbulent flow is, well, traditionally has been avoided because it's incredibly hard to mathematically model. So those areas of science that required turbulent flow, which was rapid flow in hydraulics, not hydraulics, but hydrodynamics. Weather is turbulent. You get these eddy currents, you get these bits where things are moving fast, bits where things are moving slow. If you had river beds, they'd find it easier to make a model of the riverbed and try and figure out what's going on from that. Very difficult mathematically. So if you did engineering and you did hydrodynamics, it would be very short. Your degree would be in other things more than likely. And weather was always a joke. In Britain, forecasting weather in Britain is always hard because we're at the end of the Gulf Stream. So we get the weather that everybody else has finished with, so it tends to be kind of like spottery. So it's always hard, but it was a joke. When I was a kid growing up, if it said sunshine, you'd take an overcoat. And if it said it was going to snow, you'd wear a jacket, because they were always wrong. I mean, even to within hours, they were wrong. It was like, and within 40 miles, they were wrong. It was like, and then it got better, and it got better for me because I came to the States and it was sunshine every day. I remember watching the TV weather guy, thinking, I could do that job. It's like it's the same thing every night. It's like it's going to be showers in the afternoon, but sort of the time sunny. It's like, you know. But in Britain, the weather got better in terms of forecasting, and it was all due to chaos theory, actually. Bunch of college dropouts one of them reads this article about how on an isolated island in the middle of the Pacific, when you look at populations of prey and predators, it's still not steady. All physics says that if you have foxes and chickens, eventually you will have enough foxes to eat, enough chickens to feed the foxes every year. You'll reach this steady state. 100 chickens, 5 foxes, happiness. Next year, 100 chickens, 5 foxes, happiness. It'd be like that. They'd reach equilibrium. We always go towards equilibrium because that's an equal sign, yeah? And what they find is on this island that's like been isolated for, centuries. One year there's like 100 foxes and they nearly eat all the chickens, and the next year there's like 1,000 chickens and the foxes can't eat enough. Well, sorry, no. The 100 foxes eat all the chickens. The next year the foxes starve because there's no chickens. Next year chickens breed like crazy, so there's tons of chickens. Next year foxes can eat, so they breed like crazy. Tons of foxes, and it goes on. And you think at some point there'd be this like equilibrium, and there's not. So why is it that these populations are not staying down? Well, and people started playing with it, and they started looking at very simple systems, and they would get this bifringence, this fractal behavior, and they started seeing this is like really important. You want to measure the coastline of Florida. You want an accurate measure for the coastline of Florida. Depends on how big your ruler is. If you use a 1 mile ruler, you'll get one answer. If you use a 1 yard ruler, you'll get a different answer. If you use a 1 inch ruler, you'll get a different answer. So it's like these problems with some areas of science we just ignore. If you can't do the math on it, you ignore it. So fluid dynamics falls into this. We can do the laminar stuff, but we can't do the turbulent stuff. So we'll talk about the turbulent stuff in terms of I'm going to describe that it's there. Like on a map where it says dragons be beyond this edge. It's like, turbulent stuff is over there. But there is a lot of work has been done, and we're going through that process at the moment where research is done, progress is made, but it's not in the textbooks. And bit by bit, it will start being offered in more and more graduate courses, certainly offer it, and then it'll be being offered in more and more undergraduate courses, and eventually there'll be stuff in our books about, to handle some of this turbulence. But it's in that process of being, assimilated by the teaching community. That's what's going on. But it's fascinating. It's called the butterfly effect. If the butterfly flaps its wings on the coast of Africa, it causes a high-pressure little blip, which causes a high-pressure trough, which causes a tropical storm, which causes a hurricane. And if the butterfly just doesn't flap its wings, then that little pressure is never created, so the whole thing is nipped out before it begins. Small differences in the beginning make a huge difference at the end. That's turbulence. You're going along, you're next to me, little difference in our position, huge difference in where we end up. That's turbulence. And being able to predict what goes on is amazing. So, for instance, to give you one example, so if you have a thing called fibrillation, if your heart tends to flutter, the medical community is likely to put a pacemaker in because your heart is unreliable. Well, your heart's reliable most of the time. It's like you have a fender bender, so the court says you need a driver from now on because you're untrustworthy. I had one fender bender. Well, we're going to put so you got all the expense and all the stress of having somebody driving you around. It's a bit like that with your heart. You had this one incident, or maybe two incidents of this irregular heart rhythm, and so they put an electronic master in charge of your heart, which basically says beat now, beat now, beat now, beat now. Whether your heart wants to or not, it takes over. And if you're forced to do things that you could do, but you're forced to do them not when nature says to do them, but when this electronic system says to do some, it's not very good. For most of the time, you'd be just fine. It's this avoiding of this unfortunate circumstance that could happen any time down the road. So it turns out with this chaos theory, they can look at the way your heart is behaving, and they can detect when you are beginning to start misbehaving. It just nudges you a little bit. It's like it prevents the butterfly from flapping its wing, and you avoid the hurricane. So it senses when your heart's going to misbehave, and it just gives you a little prod then, and then you don't. You just avoided this circumstance. So it's much less damaging to the heart. And that's the modern pacemakers are much more like that. So it's kind of, I find this area fascinating. But so we talk about, sorry, let's have a look. Ooh. Oh man, I made it with